it's really a spectacular program that SPE is very proud of, and we're very proud of Eve's work. Because our ability to bring this program into classrooms has been interrupted, we thought it would be a good opportunity for us to share with you a little bit about what the PlastiVan program does. And so without any further ado, Eve Vitale, take it away.
As Pat said, to have my personal photographer, videographer, who was scheduled to shoot ANTEC here to support the program today. Thanks to Mark Richardson for his help here. We are live streaming from San Antonio, actually, because no one told me ANTEC Live was canceled and we got stuck down here and are just trying to make the best of a crazy situation. Oh, that's April Fools, right? We're really live streaming from our Michigan home. A special hello to my 5 children who I hope are watching me from France, New York, Lansing, and Bay City, and my mom who is watching from her rehab and nursing center just down the road. It's hard not to be with any of you during these trying times, and I love you all. I want to give another shout out to PlastiVan sustaining sponsor Braskem, as well as all of our other SPE chapter and industry sponsors. We couldn't do this important work without you. The PlastiVan, as many of you know, is a program designed to excite students about opportunities in science and engineering within the plastics industry. Students get a look at the history, chemistry, processing, manufacturing, and sustainability of plastics and how the real world applications relate to their everyday lives. And that's the beauty of this program. If we can relate it to a kid's life and show them how drastically their lives would change without plastics, and throw in some flashy science demonstrations, we can achieve our goal of changing the perception of plastics one classroom at a time. That bit of wow was cellulose nitrate, AKA nitrocellulose, and we often use it when we're introducing the history of plastics. About 175 years ago, a German-Swiss chemist, Christian Schoenbein, was doing some experiments searching for substances that could produce ozone. He liked to do his experiments in his wife's kitchen when she wasn't there because she wasn't happy about it. And one day he spilled some nitric and sulfuric acid and grabbed his wife's cotton apron to wipe it up. He hung it next to the wood-burning stove in hopes that it would dry before she got home. Well, it went up in flames violently and with very little smoke. And voila, smokeless gun cotton was born. About 25 years later, John Wesley Hyatt in the US created a moldable material by adding camphor to the nitrocellulose in response to a need from industry for an ivory replacement. This new material, celluloid, replaced ivory piano keys, knife handles, and billiard balls, to name a few. So that's the wow in PlastiVan. Next, we make it personal. One of the exercises I take each class through is planning a school-wide party. So let's pretend that you all are in charge of getting the food for the awards ceremony, Acclaim at ANTEC. And we are all going to the grocery store together. Virtual ANTEC disclaimer. Don't try this at home during this time of social distancing. You each get to fill your cart with your favorite foods for the party. The answers I always get from students include Doritos, Oreos, soda pop or soda pop, depending on which region of the country I'm in, frozen pizza, ice cream, cookies, strawberries, juice, hamburgers, hot dogs, buns, mustard, ketchup, and bacon. You'd be surprised how often I get kids who want to throw bacon into the cart. I usually throw in carrots and dip and bags of apples and have met with groans, but I want them to realize that nutrition is important. So I get everyone imagining that their carts are full of food, and then I tell them that I am the PlastiVan lady, and I have special plastics mojo, and I'm going to snap my fingers, and everything that is plastic is going to disappear. What's that look like? It takes about 5 seconds for that mess in a grocery store to sink in, and we talk about it. After the amazement dies down, I also mentioned that we'd all be in a lot less clothes, and there's more discussion and snickering disbelief. Now that I've gotten them invested in a story that has some emotion, This allows me to get my point across. Plastics help us all live a better life and are ubiquitous. And what does that mean, class? I asked them. Plastics are everywhere. Plastics are ubiquitous. In 2019, our 7 PlastiVan educators served over 24,000 students with 169 distinct visits in 91 cities in 16 states. With the support of our sustaining sponsor, Braskem, and our major sponsors, CP Chem, Charter Next, the Detroit, Chicago, and Milwaukee sections, the automotive and color and appearance divisions, and so many more, we were on track for a 10 to 15% increase for 2020, with expansion to the West Coast, but we'll have to wait until next year to meet that metric. The PlastiVan has an amazing group of educators, whom I hope are all watching, and are dedicated to enlightening students to the benefits of plastics and the opportunities in our industry. We have a chemical engineer, a packaging engineer, a social scientist who is interested in how we interact with the materials in our world, a material scientist, a STEM outreach specialist who spent years in the classroom teaching science, a mechanical manufacturing engineer, and an organic chemist who was also a middle school science teacher. And none of us could do it without our program coordinator, Julie Proctor, who keeps us all on track. Thanks, Julie. One thing that we discuss at every visit is polymeric structure. The level of detail we go into depends on the age of the student. I've had the fun of delivering PlastiVan to kindergartners as well as to a mezzanine class of engineering students, which included both undergraduate and graduate students. Both classes reported that they learned things they didn't know and that it was worthwhile. Here are the kindergartners learning how to sort and recycle. Who knew recycling could be such fun? I don't have a picture of the college students because they weren't nearly as cute. So, 6th graders, that's all of you. Let's talk about polymers, the basic structure of plastics. Now, how many of you know what an atom is? I'm imagining that all of you are raising your hands right now, I hope. And how many of you have studied what a molecule is? One that you may be familiar with is H2O. Who knows what that is? Water, right? It's a very small molecule, each molecule only having 3 atoms. Well, plastics are made up of molecules called polymers that are very different than water molecules. As scientists, it helps us to understand words. So we're going to take a look at the word polymer. Does anybody know what poly means? Poly means many, and mer means part or portion. So polymer means many parts. We use this to demonstrate what a polymeric molecule or polymer looks like. And we tell the students that polymers are made up of monomers. Let's take a look at that word. What does mono mean? Right, mono means one and mer means part. So a monomer is one part and a polymer is many parts. Polymers are also called macromolecules. If I were teaching to high schoolers and not 6th graders, I would go over Staudinger's discoveries in the field of macromolecular chemistry that he persisted in to finally win a Nobel Prize in Chemistry in 1953, after years and years of being ridiculed and publicly attacked for his theories by other organic chemists. Some molecules can be very, very large, even hundreds of thousands of monomers long. If you could see a polymer up close, it might look something like this. And you might not really realize how long the molecule actually is. Look at the polymer in this cup. It doesn't look too big, but when we take a closer look at its length, it's pretty impressive. Let me move that out of the way. Now, let's try something else. This balloon is made of latex, which is a natural polymer. Actually, there are a lot of natural polymers in the world, and even in your body. What are some of the really long molecules in your body? Your DNA, your hair, your fingernails, to name a few. So not all polymers, those really long molecules, are plastics, but all plastics are polymers. What if I wanted to manipulate the natural polymer change in this balloon by putting a skewer through it? How could I do that? Do you think I could? Let's take a look. Do you think I should put the skewer through quickly or slowly to move those polymer chains out of the way? That's right, slowly. Do you think I should twist the skewer or go straight through? That's right, I'm going to twist it to help move those polymers out of the way. I'm going to put the skewer through the areas of the balloon where the polymers aren't stretched as much. So that would be up here by the knot and on this end. First, a little lotion on the skewer. Now, I like to tell students that if I fail, that's okay, because scientists and engineers often fail on their first attempts at something, and then we try to learn from our failures. Oh, I failed. Well, I have another one, and I don't know what I learned from that, except that these balloons have not been very good today to me. All right, here goes. I'm going to try it again, very slowly, twisting, twisting. All right, I'm in. Coming out the other end, twisting, twisting slowly. And now I have successfully manipulated polymer chains. This is where all students get to try and manipulate polymer chains by putting a skewer through a balloon. And it gets the class very excited and interested. Some students are scared to try this, and I like to tell them that there are a lot of hard things in this world, but manipulating the polymer chains in a balloon is not one of them. Through Brascom's support in 2019, we were able to introduce our new sustainability curriculum in Portland in January and Los Angeles in early March. This enhanced curriculum of the PlastiVan curriculum was a big hit. And it was the only way we could gain access to the Pacific Northwest and West Coast markets. I was able to hire 2 new educators to serve those markets, and we'll be onboarding them soon to begin their training. We usually have between 40 and 60 minutes to deliver the full curriculum, so it's pretty fast paced. And today I'm only showing you a few of our topics. Next up, I'm going to take you through our foam module. But first I have to put on my PPE, which we've all learned is very important. Single-use plastics PPE. And obviously, I can't even get my glove on. Apparently, I've had too much caffeine. Let me start with this hand. Mark warned me about having too much caffeine, but sometimes I don't listen to him. All right, this is a really popular topic with students, our foam module, because our demonstrations are pretty fun. What I'm going to do is mix 2 liquids together. A polyether polyol, 1 liquid, and a diisocyanate, 2 liquids, and I'm going to mix them together. And I colored these a beautiful green, a beautiful SPE green. You know what I'm noticing right away as I'm mixing these liquids? I'm noticing a lot of bubbles. What do bubbles indicate when we mix a couple chemicals together usually, class? The correct answer is a chemical reaction. This starts the step growth polymerization and foam generation, and the volume should increase about 30-fold. But I usually don't tell that to my students because I want them to be surprised. This creates a cross-linked polymer. I can demonstrate the cross-linking with this polymer chain. You can see here that we have our polymer chains, and when we add a cross-linking agent, these intermolecular forces connect adjacent chains to create a thermoset, which means the shape and form is permanent without additional heat and cannot be mechanically recycled. This polyurethane foam is an example of a closed cell foam, which means the gas created in the reaction is completely surrounded by the solid material and it can be rigid. Yesterday, I made this foam, which is pretty exciting, looks a bit like Pac-Man, and you can see that it's a rigid foam. Oh, and here we're watching our poly. Hopefully it will muffin over the top. I also have an example of foam where the gas pockets connect to each other, and with force you can displace the air, collapsing the foam, just like this whoopee cushion. This usually amuses the younger students to no end, and I can get the older students to laugh too, well, most of them, by telling them that when I was a kid, a long darn time ago, we had to blow up our whoopee cushions each time we wanted to use it, even after someone sat on it. But some application engineer in the toy industry figured out that we could use this material, this open cell foam, to make an improvement in a beloved toy, and it would self-inflate. That's what we get to do as engineers. Figure out how to use amazing materials to make our life better. One example, the University of Michigan has made a cartilage replacement using Kevlar and polyvinyl alcohol. This material resists shear forces and allows the Kevlartilage, that's such a cool name, to absorb water to aid in compression resistance. These type of examples get students interested in the opportunities in our industry. This cup and this cup are made of the same material, polystyrene, but this one is expanded polystyrene, which means it has been foamed and is an example of a closed cell foam. Although they are the same material, I would only drink my coffee in one of these. Which one, class? I would choose this one because the gas trapped in the plastic material is a great thermal insulator, so my hand wouldn't be burned by the coffee. Most of you, most students in my classes, likely will call it styrofoam, but that's actually a Dow trade name for the rigid foam insulation board. Since we know that there's a gas trapped within the plastic matrix, is there any way I can release the gas to see how much actual plastic material is in the cup? Can I pierce it like this? Nope, but there is a way. Don't look away. This happens quickly. And there you have it. What's interesting is look at the minuscule amount of material. Now, generally, with more time, we would have already gone over the fact that polystyrene is a thermoplastic. And again, we're going to look at that word to understand it better. What does therm mean? Yes, heat. And what does plastic mean? I have delivered PlastiVan to thousands of students around the country, and I can count the number of times on one hand, actually I think it's 3, that someone got this right. What does plastic mean? Usually gets the answer, plastic. Plastic actually means moldable, shapeable, or formable. So looking at the word thermoplastic shows that with heat, the material is moldable. We then go through a demonstration that shows the recyclability of a thermoplastic. This is a thermoplastic polycaprolactone, which has a melting temperature around 65 degrees C. I'm going to have my students describe some of the physical characteristics, which I'll do now. It's flexible, although they actually like to use the word bendy. The shape is rectangular. It's green on one side and black on the other, kind of shiny on the side. And you know, it's at about room temperature. Now I'm going to use boiling water. Hey class, what's the temperature of boiling water? I usually ask, and you'd be surprised how few students know this. So in case you're wondering, it's 100 degrees C. I'm going to use boiling water to add heat to this so that I can mold it. I like to tell the students, don't worry, hardly anyone's ever been hurt or died doing this demonstration. That usually gets them pretty excited. All right, so I'm going to take this polycaprolactone, which melts around 65 degrees C, and I'm going to put it in this 100 degrees C water. You all can let me know when it's ready. Maybe Mark can tell me when he thinks it's ready. Yep, okay, it's ready. ready. I usually have 2 students in front of the class. They're having a little contest as to who can mold the best thing. Let's see, you know, I'm going to do the simple one. I get a lot of this and mold it into a sphere. It really turns into a bouncy ball. Let's see. And I would describe the physical changes now that I've added heat. It's moldable and the colors have kind of, you know, morphed together. And as it's cooling down, it's getting less moldable, all right, because this is thermoplastic, it needs heat to be molded. All right, now that I have molded a sphere or a bouncy ball, I have to decide if I like the bouncy ball. If so, I'm free to keep it, but if not, the class has to decide what we can do with this thermoplastic. And they usually come up with the right answer. We can remelt it, we can remold it, we can reuse it. What's that called? That's recycling. And this is how we start the recycling discussion in our PlastiVan Classic curriculum with the battle cry, thermoplastics are recyclable. So now back to our polystyrene. And the question is, since expanded polystyrene is a thermoplastic, is this cup recyclable? Many students will still answer no, because they haven't assimilated the information completely yet and only know that styrofoam, the Dow trade name that they associate with EPS, is a bad material. That's what they've heard. We let them know that yes, polystyrene is a thermoplastic and it is recyclable, but the economics are tough. This is the amount of material in 1 cup. There isn't much recovered material when recycling EPS. This is approximately 15 to 20 EPS cups densified. The logistics and expense of collection and densifying for mechanical recycling or collection for pyrolysis, chemical recycling, are not always economically advantageous. When considering issues that are not easy to manage or need innovation, like end-of-life issues, we invite students with a passion for chemistry or sustainability or engineering or material selection or supply chain and more to consider the plastics industry as a career choice. I let them know that we are counting on them to join us, that we need their passion to improve the world and their ideas to make a difference. Depending on where students are located, we also try to enlighten them about local plastics programs. I was recently a guest speaker at the Ferris State University Student SPE chapter. I was telling them about the scholarship opportunities at the SPE Foundation and doing some PlastiVan demos for them. And I asked if anyone was studying plastics because of a PlastiVan visit. This young man, Carter Duran, said that he had seen the PlastiVan at his high school in Bay City, Michigan, and that was the reason why he was at Ferris State University. This is a school that the Detroit section has sponsored for many years. By having a long-term relationship with the chemistry teacher, Sandy Schaefer, we have created an advocate for our program and our industry. I talked to Sandy in December and she said, John Glenn students have enjoyed over 10 years of PlastiVan visits and have had several of our students attend Ferris State University and obtain plastics or rubber-related degrees. We don't do enough to expose kids to career opportunities at the high school level, but the PlastiVan does just that, educating my students about the great plastics careers available. I hope the program continues for years. PlastiVan makes a difference and changes the perception of plastics 1 classroom at a time. If you're interested in having PlastiVan visit your local school and or sponsoring a visit, please visit our website at plastivan.org or email me directly at foundation@4spe.org. With Brascom's sustaining sponsorship, we are able to make sure we can schedule a visit to your local school. Thank you for your kind attention today. And Ben, one of our kindergartners, says thank you too. If you have questions, you can use the chat box, and I hope to hear from all of you soon.